So, welcome back to NPTEL lecture series on total synthesis of natural products. The last 4 lectures we talked about many total synthesis of triquinanes, and there are many more methods for making 5-membered rings. So, today I will just talk about few methods where 5-membered rings can be made and also discuss one more total synthesis of triquinane. Pass-and-Kahn reaction is one reaction where routinely people use to make 5-membered rings. See, for example, if you have a double bond and a triple bond at appropriately placed, then if you treat with dicobalt octacarbonyl and followed by oxidation with N-methylmorpholine N oxide or dimethyl sulfoxide, one can get the corresponding cyclopentanone. So, depends on the ring size, you get the other ring can be 5-membered, 4-membered or any ring, but this Pass-and-Kahn reaction will give 5-membered ring. Particularly this reaction works on the other side if it is 6-membered and 5-membered. Okay, so here you have a diquinane structure, and this is another example where you can see you can put a heteroatom. Okay, it can be the heteroatom can be oxygen or heteroatom can be nitrogen. Still this reaction works well to give the corresponding cyclopentanone, and one can also use other reagents. For example, one can use Wilkinson catalyst. The same condition, you have a double bond, you have a triple bond, but here for the carbonyl source you do this reaction in under carbon monoxide atmosphere, and you also have to use silver triflate to get the corresponding bicyclic compound. One can also use molybdenum hexacarbonyl in DMSO, and if you reflex at 100 degrees you can do the same thing, and this is an interesting combination where instead of double bond you have an allene. Okay, so allene, that internal double bond undergoes Pass-and-Kahn reaction. So, you see this double bond, the terminal double bond becomes exocyclic double bond in this case, and one can also use this for a heterotriquinanes. In this particular case you have a nitrogen, and with this nitrogen one could make the azatriquinanes using Pass-and-Kahn reaction as the key reaction. And there are other methods, as I said, used for making 5-membered ring. One of the methods which is quite frequently used is vinyl cyclopropane. As you know, vinyl group attached to cyclopropyl can undergo like this rearrangement. For example, you can write like this. The cyclopropanes are like double bond, and sometimes cyclopropane, as you know, because of its ring strain, it tries to open, and if you heat it, this can undergo this type of cyclopropane, vinyl cyclopropane rearrangement to give cyclopentene. So, here is another example. So, this can undergo the vinyl cyclopropane rearrangement to give this diquinane. This is another interesting example where you have cyclopropane attached to the double bond, and the double bond is part of a 5-membered ring. So, this will give you this enol TMS ether, and one can hydrolyze this to give the corresponding ketone. If you hydrolyze this with acid, you will get the corresponding diquinine having a carbonyl group. So, this vinyl cyclopropane rearrangement also has been used to make at least 2 5-membered rings, if not for 3 or 4. Then the standard reaction which is routinely used for making 5-membered ring is aldol reaction. So, you have an aldehyde here and methyl group. So, you can generate anion here, that anion can attack this aldehyde followed by elimination of water, you can get the 5-membered ring. And same thing, you can see you have methyl group, you can generate anion, add to this aldehyde. So, that also will give a 5-membered ring. Of course, this has been used in the total synthesis of one of the triquinanes, that is a linear triquinane, and this has been used, this particular example has been used in the total synthesis of an angular triquinane. So, you can see you can generate anion and attack this aldehyde followed by elimination of water, you get angular triquinane. So, alkylation, aldol reaction, sometimes even Michael addition or opening of the epoxides have been used successfully for making 5-membered ring. So, if you look at this example, it's a beta keto ester. So, one can easily generate anion here, and intramolecular SN2 substitution will give this 5-membered ketone. Okay. So, if you decarboxylate, then you get corresponding ketone, otherwise you get the corresponding beta keto ester. The next example, you have a cyanide. Of course, because of the cyanide, you can remove this proton. Once you remove this proton using a base, maybe you need strong non-nucleophilic bases like LDA that can immediately open this epoxide to give the corresponding 5-membered ring. And this particular example is very interesting. You have a Michael acceptor and you have Michael donor. It is a keto ester, beta keto ester. The anion can be easily generated selectively. This can undergo a 1,4 addition, intramolecular 1,4 addition to form 2 5-membered rings. It is a diquinane. Now, one can remove this ester because it is a beta keto ester. So, that will give symmetrical molecule. Then this double bond can either cyclize here or it can cyclize at this carbon. So, that is how one can make angular triquinanes. So, Michael addition followed by an aldol reaction, one can construct a triquinane, and in this case it is an angular triquinane. So, there is another reaction which is called Nazarov cyclization. See, this Nazarov cyclization is nothing but if you have a dienone, okay, so like this you have, then this on treatment with acid you get corresponding 5-membered ring and more substituted double bond. You get a cyclopentenone and the double bond is more substituted. Okay. And you can also control the regioselectivity of the double bond form. Say for example, if you take this example, okay, so there are 2 possibilities. One, what I have written here. Another one, it can also form like this, isn't it? But between these two, only this forms. The reason is, as soon as it coordinates with Lewis acid, more than this double bond migrating, this double bond will migrate, and because of the lone pair here, next this double bond will migrate. So, that will give you this as the major product. So, depending on what you want, you can use a substituent in the dienone to get exactly where the double bond is required. You can also use silicon. Silicon also used to control the double bond which is required. So, for example, if you want the double bond to be here in this double bond here, so then what you do, you put a silicon at that carbon. Okay. So, now what happens? Instead of this double bond migrating, first this will migrate, followed by migration of this. So, what will happen? Silicon is known to stabilize carbocation at beta carbon. So, this is called beta silicon effect. Silicon carbon bond can be easily cleaved, okay, and particularly if it has to neutralize the positive charge at the beta carbon, then this can be easily cleaved to get this dienyl ether. This upon hydrolysis will give you this ketone. So, basically under normal Nazarov cyclization you get more substituted double bond, whereas if you use a silicon, then you can also get less substituted double bond as the major product. Okay. Then there is another very interesting methodology. It is a tandem reaction where oxycope rearrangement followed by ring closing methodology. It is almost like oxycope rearrangement followed by intramolecular Mukayama type aldol reaction. Okay. So, that also could be successfully used or has been used for the synthesis of triquinanes. So, for example, this bicyclic compound, if you treat with vinyl lithium, you get this intermediate. Now, if you look at this intermediate is a classical oxycope intermediate, So, this will give you the corresponding 8-membered ring. So, this 4-membered ring also will break, and here it will form 6-membered ring. So, overall it will form an 8-membered ring. And if you look at this particular product, in that process you have generated an enol TMS ether and also another double bond which is in conjugation with enol TMS ether. Okay, so you can call this as vinylogous enol ether. So, this what will happen, this lone pair or this silicon bond come here, this will come and this will attack the carbonyl. So, that will give you the corresponding triquinane. So, linear triquinane, isn't it? You have 5-membered, 8-membered. So, the 8-membered ring cyclizes intramolecularly to give this linear triquinane. Okay. So, what I will do, I will talk about one more total synthesis as I mentioned, that is about the synthesis of corialin. This is reported by Paul Mender's group, and interestingly what he has used is again little bit extension of the method which I discussed in the last slide, where you convert the 8-membered ring into 2 5-membered rings, and this 8-membered ring he made using 4 plus 4 cycloaddition. See, 4 plus 2 will give 6-membered, 4 plus 4 will give 8-membered ring, and this 4 plus 4 can be done using photochemical condition. Okay, how he successfully accomplished the total synthesis of corialin using this 4 plus 4 cycloaddition and also the transannular cyclization which I briefly discussed. For that, his starting material is methyl isobutyrate. So, you take isobutyric acid and then methylate that. Upon treatment with LDA, you generate anion here, and that you quench with this allyl bromide substituted. So, you introduce a diene. So, you have already introduced one diene. As I said, the key reaction is 4 plus 4. So, now you have already a 4 pi unit. You need another 4 pi unit. So, you reduce the ester to corresponding primary alcohol and oxidize that under Swan condition to get aldehyde. So, now use another 4 carbon unit, that is the corresponding lithium, add to this aldehyde, you can see you got a tetraene, okay, a diene here. So, a tetraene, and this tetraene can undergo an intramolecular 4 plus 4 cycloaddition reaction. Okay. So, the intramolecular 4 plus 4 cycloaddition it can undergo. So, before that you have to protect the hydroxyl group. You protect the hydroxyl group as mom ether, then you do this photochemical reaction. So, there are 2 ways to look at it. One, it undergoes 4 plus 4 cycloaddition, or one can think about doing a 2 plus 2 between these two followed by co-prearrangement, 2 plus 2 followed by co-prearrangement to give this cyclooctadiene. Okay, it is a symmetrical compound, cyclooctadiene, symmetrical compound. Is it symmetrical? No, because you have 2 methyl groups, mom group, it is not a symmetrical compound. Nevertheless, you can selectively do hydroboration on one of these double bonds. Which double bond will undergo hydroboration? That too, if you have to use 9-BBN. So, 9-BBN is a bulky hydroborating agent. So, obviously, it will not go to tetrasubstituted and it will go to the disubstituted, and then even disubstituted there are 2 possibilities. One, this way it will add, other one so this is A, this is B. So, obviously the addition of hydroboration will take place by A and not by B. The reason is BBN is bulky. Okay, so this side you have already methyl group, so it will not go to left hand side. So, this upon hydroboration with 9 BBN and oxidation with hydrogen peroxide you will get the secondary alcohol, and this secondary alcohol you can oxidize using PDC to get the corresponding ketone. Okay. Then you treat with BF3 ethyrate. So, BF3 ethyrate what will happen? It will coordinate here and this double bond will come, followed by elimination. Okay. So, when the double bond comes here, so you will have carbocation and that carbocation will lose a proton and you will get this. Okay. So, now you have got the linear triquinane. So, few more functional group transformations should be done. So, what are the functional group transformation? Again you have to do hydroboration oxidation. So, you have a tri-substituted double bond, and if you do hydroboration oxidation, this carbon you will get or you will introduce a hydroxyl group. Okay. So, you introduce a hydroxyl group, and once you have this hydroxyl group oxidized with PDC, you get a ketone, and basically you need to introduce a double bond here and you have to introduce a double bond. Both sides you have to introduce double bonds. So, if you treat with methyl chloride, not only it will become mesylate, but also it will undergo elimination to get the corresponding enone. Okay. So, once you have this enone, basically you need a epoxide here and you need epoxide here. That means you also have to introduce a double bond here. So, what you do? Before that you migrate this double bond here. So, potassium tertiary butoxide, you migrate the double bond, then reduce the ketone to alcohol. Now, if you treat with MCPBA, you get corresponding epoxide. Okay. Then as I said, you need an epoxide here, and also this should be ketone. So, you oxidize the alcohol using PCC to get the ketone. Later a double bond should be introduced. So, that can be done in 2 steps. First you generate enolate using LDA, and that time what happens when you generate enolate with LDA, the epoxide also will be open. So, you get corresponding alcohol. Now, this side you have the enolate, that upon quenching with this reagent where this will go to the corresponding carbon. Okay. So, this is nothing but oxidized version of diphenyl disulfide. One of the sulfur is oxidized, other sulfide is remaining as such. This sulfide upon further oxidation with MCPBA, it gives phenyl sulfoxide. This upon heating it undergoes elimination of phenyl sulfonic acid to get the exocyclic double bond. Okay. To complete the total synthesis you need epoxide here and you need epoxide here. So, this was done by treating with alkaline hydrogen peroxide. You get both the epoxides, and finally to complete the total synthesis what is required is removal of this MOM group. So, that was done using HCl-THF, and that gave the final natural product, that is coriolane. If you look at this molecule, how many chiral centers are there? 1, 2, 3, 4, 5, 6, 7, 8. Out of 11 core carbons, if you look at the triquinane, there are 11 core carbons. In that 8 are chiral centers. 8 are chiral centers. See, that is the beauty of this synthesis. Okay, so highly selective total synthesis, and here he has used the intramolecular cyclization as well as 4+4 cycloaddition to get these triquinanes. So, he reported this total synthesis way back in 1987, and he started with methyl isobutyrate, and key steps involved in this total synthesis are 4+4 cycloaddition. One can also give explanation that it can be a combination of intramolecular 2+2 followed by another electrocyclization, that is you have a diene, 1,5 diene that can undergo cycloaddition reaction. And finally, a trans-cellular cyclization takes place between the 8-membered ring diene, the octadiene. So, one of the double bond you oxidize to ketone, then you carry out this intramolecular cyclization using trans-cellular cyclization protocol. Overall, this total synthesis was accomplished in 4 longest linear steps, but the yield was not very high. So, yield was about 0.23. Nevertheless, if you look at the total synthesis of this molecule reported by Coriolis, it involved 3-4 key reactions, and these key reactions actually really worked well so that you could accomplish the total synthesis of Coriolis. Okay. So, with this we have completed the total synthesis of all the triquinanes whatever we plan to cover, and next week onwards we will start talking about 6-membered rings, and then slowly we will move to alkaloids and terpenoids. Okay. So, thank you.